Welcome back to Manish Kumar channel. So today we are going to discuss about argument of a complex number. So now you see already the complex plane x, y, x-axis, y-axis, and then any point x comma y, which is nothing but x plus iy type, where y-axis has imaginary quantity, okay, and then the point and O is origin. Then position vector, you can say OP. OP can be obtained using this is y, this is x, so x square plus y square, right? This is 90 degree. So now this is going to be your mod of z, right? And the theta is just the counterclockwise rotation from the positive x-axis, okay? So this is your modulus value, and this is your argument theta. Now if you look at the xy plane, so any point x comma y in xy plane, I'm talking about Cartesian coordinate, right? So what had happened, any point x comma y has this y, this is x, and this is assume origin, right? So now the point here is this point has unique representation. Let's say 1 comma 2 is uniquely expressed in the Cartesian coordinate. You cannot represent this point in any other way. But when we move to the polar coordinate, this is polar coordinate basically, right? R. R is the radial distance and theta is the argument. So we can say R comma theta, right? So when we move from Cartesian to polar, what happened here is the same point can be represented by many ways. Not representation is not unique, I mean to say. See here, if I move again 2 pi, so theta plus 2 pi, what had happened, I will reach the same point again. If I subtract minus 2 pi, I will reach again the same point. If I do for all integers, k belongs to z, right, then I'm getting same point multiple representation, right? So here r comma theta, r comma theta plus pi, r comma theta plus 2 pi, theta minus 2 pi, right, and has multiple representation, of course infinite representation because z is countably infinite, right? But this is not happen in your Cartesian plane, right? So this is how we are going to talk about the argument theta, right? So the motivation of this argument is whenever any work we are going to do with the complex analysis, like dealing with the functions or dealing with the integrations, then always we want single valued function, right? Suppose any function I have. So function is either multiple valued or single valued. So our job is to, if this is a multiple valued, then to make them into single valued. How to make this is in single valued is a very important aspect of your argument. That will be done using principal argument. Principal argument, right? This we will see soon, right? Okay. So we are breaking a multiple valued into single valued. The whole idea of your complex analysis is to make the function or the equations or whatever it may be, the giving the solution into a single valued, right? So this is the whole idea. So what had happened here is, so already you know modulus mod z equal to x square plus y square square root, and then argument. The theta angle between the vector OP and then positive x-axis is called the argument of z, and that is denoted by theta and argument of z. Argument of z means tan inverse y by x. Now the principal argument satisfies. So the principal argument has the range, if you see, minus pi to pi. Pi one side open, another side is closed. So in this range, theta has unique value, right? This is denoted by capital A argument or capital theta. Capital theta, whenever you see, it means the argument, principal argument they are talking about. And this has unique value. Why? Because if you see here, if in one rotation, if I rotate once only, right? So whatever the values of this function will achieve only 1 point, right? In the entire interval, only one value. If I repeat another interval from minus pi to pi, then again I'm going to get unique value. So in every 2 pi interval, I'm going to get a unique value of p, right? So that is called the principal argument, right? So here minus pi to pi, plus pi is closed, minus pi is open. So that I will get the unique value. And you see argument is not unique because of infinite value it will achieve, because of that fact that this adding this 2 pi k times plus or minus. So here argument can be written as principal argument plus 2k pi, where k belongs to integer, and theta has infinite number of possible values including negative ones, 2k pi or plus 2k pi, that differ by the multiple of 2 pi, right? And each theta values called an argument of g, and the set of all such values denoted by argument of z. Now the principal argument of z is denoted by capital ARG or theta, big theta. Satisfy the above condition, means it will fall in this range. Now let us understand the principal argument rule, how to calculate the principal argument. So different cases, if z is in the first coordinate, right, then principal argument is simply tan inverse y by x. If it is in second and third, then we have to worry much, because the principal argument in second coordinate, whatever you are going to get, you have to add plus pi to get into the correct range, minus pi to pi. And if it is in third, then you have to subtract minus pi from the argument so that you will reach to the correct principal argument. Okay. And these all are the equality condition when capital theta is principal argument is having these values. So let us see one example quickly to understand. Calculate the principal argument of the following problems. So four of them, I'm just taking one of them to solve. So compute the principal argument of minus 1 plus I, first one. So here if you see, the x is minus 1 and y is 1. So it falls under second coordinate. Using standard inverse tangent, tan inverse 1 by minus 1, and tan inverse minus 1 is going to be minus, tan inverse minus theta is equal to minus tan inverse theta. So and then tan inverse 1 is 45, so pi by 4, so minus pi by 4 you are going to get. But this is in the second coordinate, so this is not the principal argument, right? So what we have to do, we have to adjust by adding pi as per the formula. So now when you add pi, then it's going to be 3 pi by 4. So correct principal argument is 3 pi by 4. Okay. So now let us see what we are doing here. Graphical representation, if you see. So we have started with here, if you see, right. So till here pi by 2. And this is going to be pi by 4 from both the sides, so pi by 4. So this is going to be pi by 2 plus pi by 4. So 3 pi by 4, right? This is the complete counterclockwise. This is your value given in the second order, right? So how we have calculated? We have calculated pi by 4, and since it was coming by negative pi by 4, then we have added pi to get it this 3 pi by 4, right? Now if I want to calculate the theta for this, so minus 1 minus I, minus 1 minus I means tan inverse y by x, minus 1 by minus 1. So that is tan inverse of 1. That is going to be tan inverse of 1 means pi by 4. So it means that this angle is going to be pi by 4, right? Pi by 4. Okay. But if this is in the third octant. So now if you see, if I want to run from here to this line. So how much I have to travel? Till here pi by 2, and then till here pi by 2. So pi by 2 total I have run here pi, and then pi by 4. So pi by 2 plus pi by 2 plus pi by 4. So what is going to happen here? 4, 2 plus 2 plus 1, right? Pi. So this is going to be 5 pi by 4 from counterclockwise direction, right? 5 pi by 4 is not the correct answer because the range is minus pi to pi for principal argument. 5 pi by 4 doesn't come under this, right? So this is not the correct answer because this does not belongs into this range. So in that case, what the value we have obtained? Pi by 4, right? So we have to subtract pi by 4 minus pi. So what is going to get? We are going to get minus 3 pi by 4. So correct argument is minus 3 pi by 4, not 5 pi by 4, right? So what had happened here is, if you see, uh, we have to get the correct range, we have started from this direction to this line, right? So from this direction to this line, this is pi by 2 and this is pi by 4. So pi by 4 plus pi by 2 is going to be 3 pi by 4, right? And since we are running from the clockwise direction, so we are going to take negative of this angle. So this is going to be 3 pi by minus 3 pi by 4. So this will fall in this range. This belongs to this range, principal argument, right? So the basic idea is, if you see here, the basic idea is whenever we are here, we are going to move till this, like this, and from here to here, we are going to move till this to this, right? So this is from minus direction and this is from plus direction. Plus theta minus theta we have to do. So this is way we are going to cover 0 to pi, and this way we are covering from 0 to minus pi. So total range will be minus pi to pi for argument, principal argument, right? This is how the idea works. Either you have to use this correction when you are going to add plus pi in second quadrant, minus pi in the third quadrant, and or else you can have the idea like rotating from counterclockwise till pi and rotating from, you know, clockwise if you are, third and fourth quadrant, right? Similarly, you can calculate for other values. Okay. So now let us calculate the argument for this problem, minus 1 plus root 3. So you know tan inverse root minus root 3, then minus root 3 will be pi by 3, so minus pi by 3. But since this is in the second quadrant, so we need to add this pi, and then once you add this pi, you will get 2 pi by 3. So correct answer is 2 pi by 3, right? You can see this is 2 pi by 3. If you go from here also, you will get 2 pi by 3. You can go from here to till this with pi, and from here to till this with minus pi, right? So this is how the idea works for principal argument. Okay. So now compute the argument of 1 minus root 3i. So 1 minus root 3i. So we should not, if you see here, from here to here, if you run, right, then this is going to be your complete rotation, and this angle does not belongs to principal argument, right? So we are running from this to this and negative theta, and then this is going to be the argument which belongs to your range minus pi to pi, right? So this is very, very important to work with the principal argument, because the function or the value of z is unique always, and then we require this condition many places. Thank you very much. Thanks a lot.